Yes, alhamdulillah. So let's begin. I believe you can see my screen.
Yes, sir, we can see.
Okay. So in the last class, we have talked about this strided convolution. That means we will do convolution. Okay. So the basic thing that we have seen that, okay, if we have this 3x3 filter, and then what we are going to do, we are going to place it. So for the time being, let's assume that we haven't padded. We are doing valid convolution. So we will center this filter exactly at this position. So that means the filter will be somewhere over here. Okay. So this is how we have overlaid it. And then if we have a stride, okay, if we have a stride equal to 1, that means if I take a single step each time, then the next position I will be going is basically this position, right? Yes or no? That means my filter will be placed over here. And then if I want to move to the next position, where will I go? I will go to this position. That means our filter will be placed like this. Yes or no? Now what happens? So that means each time I'm taking a single step jump like this, right? Now the question is that if I take a stride of 2, okay, if I take a stride of 2, then how will I traverse? So at the very beginning, I will be placed over here. My filter will be exactly like this, and then I will do a jump of 2, and then I will be going where? I will be going to this particular position. So did you take a step of 1 or did you take a step of 2?
2.
Yeah, we have taken a step of 2. That's why this is called the stride. Okay, that means the stride value is 2. So if I take a stride value of 2, then which positions I will be traversing? I mean, I will be placing my filter. I will place it at the very beginning. I will place it here. Next position I will place it here. The next position I will be placing here, and then in the next row, where will I go? At 4
8.
or at 8? We'll
8.
go at, yes, we'll go at 8, then 6, then 3, then over here 2, then 1, then 8. That means in each direction, in the column direction, also in the row direction, I will be making a jump of 2. So for this particular example of 7x7 input matrix, so if I have a 3x3 filter, what will be my output size? If I talk about this particular output, what will be the output size? It's already given here. Yes? It's going to be 3x3. Yes or no? That means once I have placed it over here at this particular position, so I will get one output. In this case, for this particular filter, it's going to be 91. If I place over here, then I will get this second output 100. And if I place it over here at 4 position, then my next output will be 83. And then so on. If I go like this, so how many positions have I placed my filter? In 3x3 positions. That's why my output is also 3x3. So now we can see that previously we have seen if we take a stride of 1, okay, our output filter size was n plus twice p, including padding, minus f plus 1. This was basically what was the size whenever, I mean, this is the same thing. This was the size whenever we are taking a stride of 1. If we take a stride of 2, now we can see that our output filter size will be n plus twice p minus f divided by stride. S means the stride size, then plus 1, and then whatever the value you have here, you have to take the floor of it. Okay? The same thing will go over there. So that means in this case, your input size is 7. That means the value of n is 7. What is the value of p? For this example, what's the value of p? The padding size. The padding size is equal to 0. Then what is the filter size? The filter size is 3, and the stride size is 2. And then if you do this calculation, you will see that your output size will be 3 into 3. That means all the calculations are basically shown over here. Can you see it? Yes or no?
Yes, sir.
That means if I just show with an animation, so basically I have placed my filter. My filter values are 3, 4, 4, 102, minus 103. That means one after another, the filter will be placed like this, and I will be corresponding, I will be computing my filter outputs. That means the convolution output, and then I will end up with this particular output as a whole. Okay. So as I've sorry, as I've told you over here, That means for an n by n input matrix, so if you consider, if you want to generalize it, so this is going to be an n by n, let's say, data matrix, and with the S by S filter, normally these filters are odd sized, okay, and pairing value of P with a stride value of S, this is going to be your output side, as I have shown before, n plus twice P minus S divided by S plus 1, and we have to take the floor, okay, this is what we know as the floor operation. Up to this, do you have any questions? No question? Okay, so it is a small, just a minute. Okay, just a small optional note. Normally in the mathematics book or in the signal processing book, you will see that whatever the operations we have done, this operation is normally known as the cross correlation. Okay, cross correlation means basically, let's say if I place my filter at this particular position, the corresponding weight values will be multiplied like this. Like 3 will go over there, 4, then 5, then 1, then 0, then 2, then minus 1, then 9, then 7. This is actually how the weights are being multiplied with each other. But normally, the standard convolution operation that we are doing is what we do, we rotate this filter 180 degree. So if I rotate this filter 180 degree, how will your filter look like? Your filter will look like 5, 4, 3, then we will have 7, 9, minus 1. Then here we'll have 2, 0, 1. So this is actually how your filter will look like after you have done a 180 degree rotation. And then these filter values, are being multiplied with the corresponding input data. For example, here we'll have 7, then 9, and minus 1, then 2, 0, 1, and 5, 4, 3. This is actually how we do this convolution if we are doing convolution with this particular filter. Do you understand the difference? Yes or no? Have you understood? Nobody is saying nothing. Okay. So that means in the standard convolution operation means rotate the filter, then apply it. But remember what we are going to do, we are not going to follow the convention. Our usual convention is going to be like we have seen before. Okay, we don't do 180 rotation. Whatever the filter we have, we simply apply on this input data. This is what we will follow. Okay, this is what we are going to follow for convolution. So that means though we are saying convolution, basically it is the standard cross correlation operation. Okay, now let's talk about convolution over volumes. So far, the input data, how many channels did we have for this input data?
Only one.
Only one. Let's say if I look at this data matrix, so the size is basically 6 into 6, and that's it. The filter size was also 3 into 3. We didn't have any additional channels over here, but normally what we'll see, let's say from the point of images, normally we have an image, let's say image size is 6 into 6, but we know that there is another channel, that is the red channel, then the blue channel, and then the green channel, right? Yes or no? Do you understand what I'm saying?
Yes, sir.
Okay, that means it will be something like this. You can draw another one. That means the first channel is the red channel, then the next one is the green channel, the next one is blue channel. Or if I just simply generalize like this one, that means we'll have the first channel, second channel, and then the third channel. So if I separate all these channels one after another, how will it look like? That means your input image was 6 into 6 into 3. If I separate all these channels separately, or if I say these layers, so this will be 6 into 6 into 1. That means the first channel. Then you will have 6 into 6 into 1. That's the second channel. And then you will have another 6 into 6 into 1. Okay, 1 channel, 2 channel, 3 channel. So if you combine them all together, that means if you not summation, this is not summation. Rather, if we append them one after another, then basically your whole data matrix will be 6 into 6 into 3, right? Okay, so how do we do it? So this is called convolution over volumes, similar to what we have done before. So that means, as you can see from this particular image, your input size is 6 into 6 into 3. That means you have 3 different channels, one after another behind. Okay. Similarly, what we have seen in case of the filter, previously the filter size was 3 into 3, but now we'll also have 3 channels for that particular filter. That means if I ask you, how many weights do I have in the filter? How many weights?
3 into 3.
Yeah, that means here we have 27 different weights over here, right? Yes or no?
Yes, sir.
So if I look at this filter, it itself looks like a small volume, right? And then
Yes,
how
sir.
will I do this convolution operation? How will you do this convolution operation? The same way that you have done before, we'll do the same. For example, you can see that the input data, it has been shaded with a light color, light green, light red, light green, light blue, and the filter colors are shaded with light dark red, dark green, dark blue. So that means basically these filter values 1, 0, -1, they will be basically applied on which channel? Separately on the red channel, something like this. Understood? And if I look at the green channel, though you can see the green channel, let's say the green channels are for the filter. It is something like 1, 2, 3, 4, 5, 6, 7, 8. Just an example I'm just giving you. Then those corresponding weight values will be multiplied by the associated input values from the green channel of your input. Yes or no? Similarly, the blue filter, if I look at the blue filter, so if I draw my, let's say this was the green part of your filter, let's say if I that's it right like this, let's F green, then this is the blue part of your filter. Then the blue part maybe have another different kind of filter set. Maybe let's just example 1, 2, 3, 4, 5, 6, 7, 8, 9. This is just a different one. I just want to show you something. Or maybe I just change it like 3. Doesn't matter what weights we have put over there. So if I set those values, so basically what we have to do, we have to compute the element-wise product and then sum them up. And then if we sum it, maybe we have a correlation value or convolution value of 2, and this is the value that we store in the output. So this is what we are saying, this is my output. So is the convolution operation on volume clear? Yes or no?
Yes, sir.
Okay. So now you can see that the filter size, the number of channels in the filter size, it has to match the number of channels of your input data. If it doesn't match, can you do the convolution? Yes or no? Let's say if I have taken 3 into 3 into 2, then how many weight values do we have? You have 18 different weights, right? That means as if you don't have the blue channel. Forget about the blue channel. Okay, let's discard that one. Then can you do core convolution operation with this filter on your input? Yes or no?
No, sir.
No, because the red channel of the filter will multiply with the red channel of your input. The green channel of your filter will multiply with the green channel of your input. Then since you don't have any extra channels, then what will be multiplied with the blue? We don't have anything, right? Since we don't have anything, so basically you have to have 3 channels. That means the number of channels of your filter, it has to match the number of channels of your input. So that's why I have the next slide. So you can see over here, the number of channels of the filter, this has to match with the number of channels of the input. They have to match, okay? These two, they have to match. Okay. So since we have matched them, now we know how to do the convolution with volume data. Or let's say for this example, they have given the example RGB, since we are mostly working with RGB images as input, but it can be for any number of channels. Okay, it can be for any number. Let's say if the number of channels here, you have 4 channels, then in the filter, how many channels do you need to have? 3 or 4? It has to be 4, right?
Yes, sir.
Okay, good. Now, once we have done this convolution on volume data, what will be the output size? So here we have the output. What's the output size? What's the output size? What, nobody can tell? It's already written here. The output is 4 into 4, right? Okay, why not 4 into 4 into 3? Why not why only 4 into 4? Can someone tell me? Let me pick someone. Let's say Hafso Muhammad. Can you hear me? Are you in the class? Then the person above, I can see Fatimatu Conte. Can you hear me? Please unmute your microphone. Okay. Khalid Kamara. Okay. Nobody's answering. What's the problem? Khalid, Tarek Khalid, can you hear me?
Yes, sir.
Okay. Now you will have to answer me. So the output size is 4 into 4. Why not 4 into 4 into 3? Can you tell me?
So because you are picking first center.
Okay. That's true. So let's say for this particular example, if I look at my previous example, what we have over here. So if I remove, okay, let's have the other picture over there. Okay. So here I have 6 into 6 into 3. My channel is also 3 into 3 into 3. So if I place this volume just exactly at this particular position, okay. So it's something is going somewhere behind 2. Then the correlation value, do I have a single correlation value or I have a set of correlation values? Khalid?
Yes, sir. Second year bit.
So if I place this filter, this volumetric filter at this particular position, okay, the cross sign I have given over there. So if I do this convolution, how many values will you return? Will you return a single value or will it return a set of values?
Single.
Single value. That's why we have placed this single value stored over here. Now, if I move my volume to the next position, let's say if I place it to the next position, if I take a stride of 1, that means I have placed my filter like that. It's going behind. Again, if I do the convolution, how many values I will return? A single scalar value, and I will store it here. So in this way, if I traverse throughout the whole input, so I will traverse placing my filters at those positions. So you can see that how many outputs will I get? I'll get 16 outputs that have been arranged in a 4 by 4 matrix fashion, right? Yes or no?
Yes. Yes, sir.
Okay. Now this is what happened if I apply with a single filter of a size 3 into 3 into 3. How about, so let's say the filters are something like this. So the red filter shows the values like this, green filter shows the values like that, and the blue filter shows the values like this. And all together they have combined a size of 3 into 3 into 3. If I take another, so this is what happens that I just explained that if you place the filter all over to different places, okay, so you get the filter outputs, right? So if I take another set of filters, now what I have done, I have taken another different kind of filter. That means not only I have taken one filter, I have taken another filter. Let me draw like this. Okay, let me see. I have taken another filter, and those filters. Let's see if I draw. This is red 1, green 1, blue 1, and then the second filter red 2, green 2, blue 2. So that means I have given you another filter. So this is, let's say, filter 1, and this is filter 2. So if instead of taking filter 1, if I take filter 2, do you think you will get the same size output? Yes or no? Yes.
Yes, sir.
But instead of taking filter 2, if I had taken filter 1, I will have the same size output. But the difference now is that with filter 1, the set of values I will have 4 into 4 into 4. And then if I apply filter 2, what will happen? I will have another 4 into 4 into 4, right? Yes or no? So how many values do you have? With filter 1, I have got 4 into 4 into 4. For filter 2, I have got 4 into 4. So if I append them one after another, don't you think you are going to have a matrix size of 4 into 4 into 2? Yes or no? Yes. So if I take 10 filters, if I take 10 filters, like as you can see from this particular picture, with this particular filter, which detects the vertical edges, it will give one output of 4 into 4. If you apply the second filter, filter 2, it's also the same side, 3 into 3 into 3. I will get another output, convolution output. And then if I stack them one after another, or if I append them one after another, my combined output is going to be 4 into 4 into 2. Right? So if I had taken this, if I had taken another filter, okay, if I had taken another filter, that's also a volume basically. So you will have another output of size 4 into 4, right? And if I stack them together, what will happen? Don't you think you will have another layer of output? Yes or no?
Yes, yes.
And then your combined output size will be 4 into 4 into 3, right?
Yes, yes.
Okay. So that means if I have applied 10 different filters, then your output size would have been 4 into 4 into 10, right?
Yes.
Okay. This is actually what we have done. We have applied this volume filter. Okay, we have applied this volume filter. Also, we have taken multiple filters, and this ended up with several outputs, right? Yes or no? So here we have a small animation. Let's say if you look at this particular output, okay, this particular output for a single filter. Remember, this is for a single filter. So that means the red channel filter values will give you one set of output. The green channel filter will give another value, and the blue channel filter will give another value. Since we are doing volume convolution, what will happen? All these values will be added up, right? Yes or no? What happened? Yes or no? Okay. So that's why we have, let's say if this input was 6 into 6 into 3, and then you can see that this channel, they have separated the 3 different channels. You see, this is going to be 6 into 6, this is going to be 6 into 6, this is going to be 6 into 6, right? And then similarly, the filter side, if you separate the 3 different channels, so you have the red channel, green channel, blue channel. If you do individual convolution, and then you have to add it up, and then you can see that there is another extra term, that is the bias. Can you see the bias over here? Yes or no?
Yes, sir.
So these bias will be added for all the different filters or that particular filter. What do you think? What do you think? So where is my picture? Wait. Just a minute. Where is my other picture? Where did it go? Just a minute. What happened? Just a minute. I think I'm having some technical problems. I believe you can see the screen.
Yes, sir.
Okay. So what we have found over here, and we know that how to do this volume convolution, and only from this convolution, that means at the filter weights, let's say if I draw like this, the filter weights Wi is multiplied with the input values, let's say xi, and since we're taking the sum of products, so we have this product weight. Let's say for this example of 3 into 3 into 3. So how many filter values do you have here? We have 27. So the value of I will range from 1 to 27. Now these are what we have. The filter weights is coming over here. This is the input values. Okay. Now we know that we can also add another extra bias term over there. Yes or no? Let's say the bias value is -1. So what we see, these 2 is only the convolution value. So if I include the bias term, so instead of 2, what will you save here?
1.
1. That means you will save 1 because now I have included this bias term over here. Now let's say For example, if I place my filter at this particular position, that means you will have this whole volume over there. It will go something like this. Okay. And let's say for this particular position, that means we are looking for this particular output cell. Your convolution result is something like 5. So this is what we have found. This part has given you a convolution value of 5. And once I include the bias term, then instead of saying 5, what will you store? 4, because including the bias, we have 4. So you can see that this bias term has been added with the convolution output. Yes or no? Yes. So this is actually, as you can see from this particular image, in the next slide, in this particular slide. So once if you look to this particular output, okay, this is what we are looking at, the output values. So once you have done all these convolution, this convolution came from these 3 different channels, you add them together, and also you have included what? You have included the bias. That means once you roll over throughout the whole image, as you can see from here, once you roll over, what will happen? In the corresponding output, you store them, but it also includes the bias, right? Is this understood?
Yes, sir.
Yes, sir.
Okay. So this is what that means. Once we have done convolution, we have also, that means you have to remember that for this particular, let's say for this particular filter F, whatever the convolution result you have here, you have this convolution result. If I write like this, the convolution result plus what you have included. We have included the bias. Similarly, over here, whatever the convolution result you have got, you have to include also the bias. So if I ask you, for all the output values in this particular output 4 into 4, did we have the same bias added or did we have different bias added?
Same bias.
We have the same bias added. So if I have 2 different filters like here, okay, this one, that means if I apply this filter over here, then with this filter, whatever the convolution result I will get, I will also include its own filter. Let's say I will include bias 1, and then this is true for all the values over here. Similarly, if I pick another filter, as you can see from here, if I pick another filter, I will do this convolution, and for this second filter, I will have another filter bias 2, and this bias 2 will be added with all the outputs, and then we get the values over there. That means for each of the filters, we'll have its associated bias term. Understood?
Yes, sir.
Okay. And that means if I have 10 different filters, then for each of the filters, you will have their corresponding extra bias term. Okay. Now, if I ask you, let's say I am doing this volume convolution with, let's say, 2 filters. Even if I take like this example, how many parameters do you need to find? Since we need to find these weight values, how many parameters do you need to find?
With bias or without bias?
With bias. First of all, for a single filter, for this particular example, for this single filter,
7 plus 2.
yeah. So if I say for this particular filter, if I want to apply this particular filter, okay. So basically, what we have a weight of 3 into 3 into 3, right? And then we have an extra bias 1. This is the number of weights you have to find for a single filter. And how many filters do we have here? In this example, how many filters have we applied? 2. That means multiplied by 2. So this many parameters you have to find, right? Yes or no?
Yes, sir.
Okay. So next we have these pooling layers. So the pooling layers is similar to convolution, but it is not exactly convolution. So what we do, let's have an example. Like let's say we have this filter. Let's say 2 by 2 filter. Now remember, it's a 2 by 2 filter, and this filter is basically what we know as the max filter. So how will we apply? If I place this filter right over here, so but in the filter, I didn't give you any weights, have I? I don't have any weights. I simply overlay this filter on the input data, and then I simply compute the maximum value among them. What is the maximum value at this particular region?
9.
9. So this is what the value I will store in the output image. Then if I take a stride of 2, okay, remember I told you I have taken a stride of 2. Where will your filter go? Your filter will go here, right? Yes or no?
Yes, sir.
And then if I compute the max, what's the maximum value? It's 2. Next, I will move over here, and then the maximum value is 6, and the remaining one I have here, the maximum value is 3. That this is basically your output. So what is your output size? What is your output size?
2 by
It is
2.
basically 2 by 2. Though it looks confusing, right? 2 by 2 and 2 by 2. Okay. If I give you this example in a different way, okay, just forget about this one. Let's say instead of a stride of 2, if I take a stride of 1, for the first position, what value will you have? You will have 9. That's for sure, right? Then if I move this filter, at the stride of 1, your filter will go over here. Yes or no?
Yes, sir.
And what's the maximum value?
9.
9. And then if you move further to the right, you will come over here, right? Yes or no? And what's the maximum value?
2.
2. That means you will have to have another position over there. This is going to be 2. And then if I go over here, what's the maximum value? 9.
9.
And then if you go over here, what's the maximum value? 9. And if you go over here, what's the maximum value? 3. Yes or no? And then if you go over here, what's the maximum value? What's the maximum value over here?
6.
6. Then if you move another to the right, 6. If you move further to the right, it's going to be 3. So what's the output size?
3 by
3
2.
by
3 by 3. So it all depends on what is the stride value you're picking and also what filter size you're picking. Again, if I think in a different way, okay, if I think in a different way, let's say if you have a filter size of 3 by 3, okay, that means your filter is not 2 by 2, your filter is 3 by 3. Now, if I place my window over here, what's the maximum value?
9.
9. Then let's take a stride of 1. Okay, then I will take a stride of 1. I place my filter like this. What's the maximum value?
9.
9. Then if I move further down, maximum value?
9.
9. And then, of course, in this case, it's always 9. That's what you can see. And then if I have over here, what's the maximum value? It's 9, right? So what's the filter size, output size?
2 by 2.
It's 2 by 2. I believe you understand what this max pooling is doing. Yes or no?
Yes, sir.
Okay. Now let's see what max pooling does. That means this pooling layer is going to do is going to reduce the size of the input. Okay. Initially, what was the size of the input? It was 4 by 4. And once I have done this max pooling with 2 by 2, what happened? Your output size is what? Is also 2 by 2. Yes or no? So basically, you can see that a 4 by 4 input data has been reduced to 2 by 2. Yes or no?
Yes, sir.
Okay, fine. If that's the case, then can I say that I have somehow I have downsampled my input data? Can I say like this? Can we say like that?
Yes.
Okay, let's say I create this block. For this block, it's 9, it is 2, and then it's 6, and then here it's 3 for a 2 by 2. And then it's saying that basically the features we are extracting, that means from this block, we are only taking 1. Instead of 4 values, we are taking which value? The maximum value. That means whatever the feature values I have, I am basically taking the most dominant or most significant value. Can I say like this?
Yes, sir.
And then for the next block, what I have done? The most dominant value, that is 2. That means you are picking the features which are basically more dominant. Yes or no? At the same time, what we are doing? We are reducing the size and we are making half. It was 4 by 4. And then if I divide it in both sides, the output is going to be what? The output is going to, so this is the output. If I take it, the output is going to be 2 by 2. So if I reduce the size, what's the benefit? our computation will be less, so we are speeding up the computation, that's for sure. At the same time, we are taking the important or dominant features. So is the motivation of max pooling clear?
Yes.
Yes, sir.
Okay. So this is actually what we have. So now the interesting thing is that, as I've said, we are doing, let's say if I say like this, we are doing this max pooling with a 2x2 filter. Are we exactly doing convolution? No. Because in the convolution, we compute the sum of products, right? But did we compute any sum of products here in case of max pooling? No. Now, in case of filter, now let's talk about the filter. Let's say the filter size was, let's say 3 into 3. Now, in the input data, if I have extra channels, let's say we have a 5 into 5 into 3, let's say the number of channels is 3, then what should be your filter size? In case of normal convolution, what will be the filter size? Three into, and then this 3, and they have said that it has to match with the number of channels of the input data. Okay, this is what we know in case of normal convolution filter. But now we are doing max pooling. Okay, in case of max pooling, let's say we pick a 2x2 filter. Should I take 2 into 3? Yes or no? Should we take 2 into 3? Do you understand my question?
Yes,
Can you repeat the question?
So in case of normal filter, we have seen that the number of channels of the input data is needed to match with the number of channels of the filter. So this is your filter. This is your filter. So if I define my filter size to be 2x2, and since we are using volume data like this, okay, let's say we have 2 channels. Let's say, for example, here the number of channels is 2. Then, do you think your filter should have a size of 2 into 2 into 2? Let me draw another color. Yes or no?
Yes, sir.
No. This is not the case.
sir. We will not take the volume max. We will take this layer of the max.
Exactly. What we are doing, let's say we have 2 channels. The first channel you can see, and there's another channel behind it. So in case of max pooling, what we do, as I said, we are reducing the input size. How? We'll only apply this 2x2 filter, as you can see separately, first on this input channel of channel 1, and then again we'll apply it separately on the second channel. So you can see that the number of channels will remain the same. Okay, is this understood?
Yes, sir.
That means in case of volume convolution, normally the filter size is going to, should have been 2 into 2 into 2. If it was like that, then your output would have been 3 into 3 only, right? Yes or no? Because as if you're computing the, let me pick a different color, as if you're computing the maximum over how many volume, how many values? Several values, right? But we are not doing this. This is not what we are doing. Okay, we are not doing that. Rather, what we are doing, if we have 2 channels, we have this 2x2 max pooling. That means we do it separately. Remember, we apply this as if we are applying it separately. Is this understood? This term.
Yes, sir.
Yes, sir.
So that's why the number of channels remains the same. It is 2. So if I ask you, let's say if the input size was 4 into 4 into 5, this is what your input was. Okay, and then if I have a max pooling layer of 2x2, what will be, okay, 7 by 7, okay, looks a little bit odd for this particular case. I want to make this computation simple. Let's say it is 8 by 8 for the time being. Okay, so after doing this max pooling, what will be your output size?
4 by 4 into 5.
It is going to be 4 into 4 into 5. And what is the size of your max filter?
2 by 2.
It's 2 by 2. Is this understood by everyone? Yes or no?
Yes, sir.
Like I've
Yes.
said, max pooling is not directly similar to convolution. Because in case of convolution, the number of channels of the filter should match the number of channels of your input data. Okay, but this is not the case for convolution. Sorry, for max pooling. It's different from convolution. What we do, the size is fixed. So if this is the case, now we can see that this is what happens. Let's see if I pick a 3 by 3 filter for this particular example. Okay, instead of taking a 2 by 2 filter, let's say I have taken a 3 by 3 max filter. Can I take a 3 by 3 max filter? Yes or no?
Yes, sir.
We can do it, right? No problem in that one. Okay, we can have a 3 by 3 max filter. It will just simply traverse like that, and separately for each of the layers, it will compute. Okay, it will compute the maximum. Okay. So this is what we have. Yes. So,
Max filter.
sorry, can you repeat it again?
Sir, if the max filter. Hello.
Yeah, yes.
Sir, here the max filter is 3 by 3. If we use straight value of 2, are we
Okay.
discarding the rightmost 2 column?
Okay. Now you can see that the equation for finding the output value is same, as you can see over here. Can you see over here?
Yes, sir.
Okay. For this particular example, what is your input size? 5 by 5, right? And then channels are there. So the value of n is equal to what? 5. Do you have any padding? We didn't take any padding. So let's say we are doing valid padding. So it's 0. What's the filter size?
3.
3, 5. What is the stride value?
2.
Sorry, what is the stride value? Look at this one. What is the stride value?
Sir, we are going to use 2.
We have used a stride value of 1.
So here we are using 1, but
Yes.
if we use 2.
Okay, if you use 2, what will happen? Then divided by, you can see divided by what? The stride value of 2. Yes or no?
Yes,
This is what you have picked. Then 5 minus 3, what do you have? 5 minus 3 divided by 2 plus 1. Take the floor. 5 minus 3 is what?
2, sir.
2 divided by 2 plus 1. What do you have here? It's going to be 2.
2.
That means your output size is going to be 2 by 2.
Yes, sir. But if we use this straight value of 2, are we discarding the one of the columns of the input layer?
That's exactly
Because
what we do
how
in
do
case of
we?
stride. This is exactly what we do for stride. Let's say if I look at this thing. Let's say for the stride value of 2, your filter was initially where? Initially here. Yes or no?
Yes, sir. Yes, sir.
Okay, fine. And then you have placed yourself here. If you make a jump of 2, where will you go? You'll come here? Yes or no? Right?
I will go at 1.
You're jumping, making it 2. You have a stride of 2. And then if you want to move to the next position, where will you go? You will come over here. And then if you make another jump, where will you go? You'll come over here. So how many positions have you visited?
Yes, sir. Yes, sir.
So your output value is going to be 2 by 2. Yes or no? Right? And then if you have, let's say if you have 3 channels, then your output size will be 2 into 2 into what? 3. Understood? Is it clear?
Yes, sir.
Okay.
Yes, sir.
So this is what we have done. So now you know that how these max pooling are working, right? Now you can see that if you have, for this example, you have a filter size of 2 by 2 with a stride of 2, then this size input will change to that size output. So you can see that the number of channels are same, right? The number of channels are same. Okay. So there is another kind of pooling that is known as the average pooling. That means instead of doing the maximum, what we do? We compute the average. For example, if we have this 2 by 2 filter, this is the average filter, right? This is the average filter. Okay. So if I place it here, previously the output value was 9. I have picked the maximum. But now what we are doing? We have to compute the average of all these 4 values, and then you store the average one. Similarly, if you have a stride of 2, you see here, you have a stride of 2, you will place it over there, and then what will happen? You have 4 values, compute the average. You have 4 values, compute the average. Here you have another 4 values, compute the average. So this is what you have after you have done average pooling. Understood? But more often you will see that people are using this max pooling so that we can get the dominant filter response. Okay? But you can also see some authors, they have used average pooling. So average pooling is you simply compute the average. Why they have done it? Maybe it can happen that all these are zeros, and then here you have 9. So what will be the maximum value? The maximum value would have been 9, right?
9.
But if I take the average, what will happen? The average value will represent the whole data to some extent, right?
Yes, sir.
So there are different ways of doing this pooling. The most common is the max pool, and another one is the average pool. Okay. So now, in summary, we have seen that the parameters, that means the hyperparameters that you have to tune during the training stage is either you can pick this filter size, the stride size, or the filter type. That means it can be max, or maybe it can be average, or it can be anything else. For the time being, let's say we haven't done this padding. Normally you see that they don't do this padding, but you can also incorporate padding. But more often you see that they don't do this padding. Now the question is that in these filters, the max pool filters or average pool filters, do we have any weights to define? Is there any weight?
No, sir.
No. If there is no weight, that means basically during this training stage, that means during this optimization steps, that means if we want to use this gradient technique, we don't have any parameters to learn. So this is one of the benefits of using max pooling. First of all, you can get the dominant features, you can reduce the input size, and also during this training step, you don't have any parameters to learn. So this is the benefit of using max pooling. Which one you said? From where? We don't have any weights actually. For which cases? For convolution layer or for pooling layer? For which layer are you talking about? So how do you, I mean, as I told you before, in case of max filter, what we do, if I look at this particular example, what have you done? We have defined a filter. It's not an ordinary filter, it's a special kind of filter. So there is no weight associated. There is no weight. What we do? We simply overlay this filter on the top of your input. It will get a certain portion of your input. And from here, what we compute? Let's say if it's the max layer, what will happen? The output will be what? 9. So do we need any weight here? No. But what are the other parameters you have to tune? Okay, weight is not there. Okay, weight is not needed. Let's say is not needed. This is one benefit. But what do you have to pick, or what do you have to choose? Filter size. Let's say this filter, instead of having this 2x2 filter, I could have got a 3x3 filter, right? Yes or no? And then you can also pick the stride size. It can be stride 1, it can be stride 2, or stride 3. Yes or no? And again, it can be either max filter or it can be minimum filter. Oh, sorry, max filter or average filter. Yes or no? But these things you do have to pick. Yes or no? That means you have to have these parameters. These are the hyperparameters that you have to pick. And how do you pick these hyperparameters? With which dataset do you pick the hyperparameters? With which data do you pick the hyperparameters? Using the validation set, can you recall? Yes or no?
Yes, sir.
Yes. But during the training step, do we need, I mean, once you're doing this training, do you or can you change the filter values A for S? No. So when do you change? Once you're doing your training with a different kind of data, that means the validation data, then you see whether 2x2 filter is okay or whether 3x3 filter is okay. Those are the options that you have to pick during your validation data. And we know that which parameters are known as the hyperparameters. I have taught you before. Which parameters are your hyperparameters? The parameters which are fixed during the training stage, but which can vary during the validation stage, those are basically your hyperparameters, right? Yes or no?
Yes, sir.
For example, the number of hidden layers. Is it a parameter or is it a hyperparameter?
Hyperparameter.
Why is it hyperparameter? Because during the training stage, let's say if I have picked 2 hidden layers, let's say you have this input layer, you have this hidden layer 1, you have hidden layer 2, and then let's say you have your output layer. So during this training stage, what do you have? These 2 parameters are fixed. 2 is fixed here. Now, if you change it, let's say instead of 2, you pick 1. But during the training phase, can you change it to 2 to 1, or it is fixed during the training stage? It is fixed, right? So that's why this is a hyperparameter. That means the number of hidden layers. Similarly, during this convolution operation, the filter size, is it fixed during the training or can you change it? Filter size, let's say if we're talking about this convolution operation. Filter size.
In training stage, we cannot sense.
Yeah, in training stage phase, you cannot change it. That's why the filter size, whether you in a particular layer, whether it's 3x3 or 5x5 or 7x7 or so on, during the training stage, you cannot change it. But during the validation set, you can choose whether 3x3 gives a good result or 5x5 gives a good result or maybe 7x7. That's you pick during this validation stage. That's why these are known as hyperparameters. Understood? Okay. Okay. So I think the time is over. Yes. So up to now, what have we learned? We have learned about different kind of operations like convolution and then max pooling. Okay. So in the next case, I will be showing you a simple CNN example where what we do, we have, let's say we have this input. Then what we have done the convolution first, and then we have done this pooling, max pooling. Again, we have done convolution and then max pooling. And then what we are doing, we are basically doing the flattening operation. I'll talk about this later. And normally in case of convolution neural network, a convolution followed by a pooling, these 2 layers together, this is known as a single convolution layer. Understood? So if I say how many convolution layers do we have here? We have 2 convolution layers. Inside this layer, we have a convolution stage and then we followed by a pooling stage. Is this understood?
Yes, sir.
Okay. So I will talk about that in the next lecture. Don't worry about that. Any questions up to now?